The morning session. We'll probably take just about half an hour or so, and then we can spend another half an hour just having a general conversation on any topic you want to talk about. So, is there anything you want to ask? Nothing? Everything is good? Yeah, go ahead. Can you take the microphone? Because of the fan, I can't hear very well.
Professor, this is regarding about the reinforcement learning.
Yes.
So we see that RL learns from the data which is coming from the environment, right? Actually, so there are like when you see a conventional MPC model predictive control, like where we have adaptive nature of the model, when the process conditions are changing, actually.
Right.
So in the case of reinforcement learning, actually, so when the process conditions are changing, and we also have to shift the set points or the optimality. So how does the RL is robust to these conditions, like
Right, because
challenges?
it's constantly exploring the process, right? The goal, it has a reward function. So for instance, in the context of control, your reward function could be negative square of control error, right? Or control error over a certain period of time. Now, it's constantly looking at that. If your underlying process changes and these errors grow, then it'll start exploring again. And when it explores, it generates new data. From the new data, it learns the new process model, and it updates its policy. So I think that's the beauty of reinforcement learning. There are a lot of connections between reinforcement learning and what's called dual control. That's a very old concept developed in the 1960s by, I think it's a Russian mathematician, Feldbaum. And MPC is actually some approximation of that. And there are also connections between MPC and reinforcement learning. But the way it works is it's constantly exploring, right? If it's away from its if it's not, if there's an opportunity to further maximize its reward, it is going to explore, constantly explore. That's the difference. If you have an MPC, there is no off-the-shelf MPC algorithms don't have an exploration tool in them, right? There are ways you can do it, but most off-the-shelf MPC algorithms don't have an inbuilt exploration. Reinforcement learning comes with an inbuilt exploration. All right. Any other questions? Okay, so if not, there's something that I don't remember who, but somebody asked me if we could talk about large language models. A couple of students asked me about how algorithms deal with non time series data. And my response was machine learning tools under the hood, they're all using some numerical calculation. Which means when you have text data or video data or pictures, whatever you have, at the end of the day, you have to turn those So in the next half an hour to 40 minutes, I wanted to show you how these language models work, what is self-attention, and what a transformer is. Obviously, half an hour is not a lot of time to discuss all of these topics, but I'll give you a high-level intuition into how these models work. That's pretty much what I want to do. Now, I think I mentioned this in the morning. I'm not sure if everybody yesterday, after going back in the afternoon, I never taught a lecture on language models, although looked at them, studied them very briefly. I never gave a lecture, and which meant I didn't have slides. So I asked Claude to create 25 or so slides on large language models using material from Sebastian Raschke, if you're interested in getting some good material, check out his books, his blogs, etc. He writes a lot about large language models. Sebastian, I think he's at Wisconsin. So he has a lot of stuff. Claude is like ChatGPT. It's another language model. It actually, I was to my utter surprise, Claude generated a really nice 25-page slide deck using Beamer in LaTeX. But some of the figures were fuzzy or sort of overlapping, and so after trying it for 3 or 4 hours yesterday, I abandoned that approach. Instead, I know that this other guy, Jay Olamar, he has some really nice videos on all things related to large language models. So check out his website. But what I want to do, he has not only videos, but he has these nice animations. I'm not sure how much time they spend. Maybe these animations, but these are really cool. So we'll go through these animations and we'll have a conversation there on how large language models work. Sorry. My speakerphone is on. This one? Yeah, no problem. Sorry about that. Okay. Now you can hear it. All right. Now, so the story starts with simple sequence-to-sequence models. Okay. So you're given a sequence on the left-hand side, a sequence of text in some language, let's say, and you want to turn that into a sequence of text in a different language. Okay. So in this animation here, there are 3 words on the left-hand side, and then you're generating 4 words on the right-hand side. So depending on the language, you'll have very likely you'll have different number of words on those 2 sides. Right? So as an example, if you take a neural machine translation model, sequence-to-sequence model. Now here you have a sentence in French. Does anyone here know French? No? Okay. I don't know French as well. My kids know French. And that's translated to, I am a student. Okay. Now what we want to know is what is under the hood. What is this model? How are they doing this? Right. So everything is really nicely animated here. Right. So typically these neural machine translation models, they have what is called an encoder and then a decoder. Okay, so including large language models, they all have in some form or the other an encoder and a decoder. The encoder is a neural network, and the decoder is also a neural network. So this word here in French is encoded, and it creates a context. Okay, a context, you can think of that as some transformation of the given French sentence, right? It creates a context, and the context is based onto a decoder, and the decoder generates the corresponding sentence in English. I am a student, okay? So this is the typical machine translation structure. Encoder, decoder, and the information from the encoder is passed on to the decoder. Okay. What's the context? The output from the encoder is called the context. The context is essentially a set of numbers, a vector, right? We're going to talk about how the words become numbers, right? How do they become numbers? Inside the encoder, you're only dealing with numbers. There are no words, right? So we use what are called word embeddings. There's a unique mapping between every word and a high-dimensional vector. So I'll talk about that in just a moment. But the output from the encoder is not a word. It's not a sentence. It's just a context vector. Okay? So these vectors couldn't be very large in this case. In this example, we're only showing a vector of size 4. Okay. And here is the representation of each of those words as vectors. Okay, this is, again, this is an example. You only have, so I don't know how to pronounce this. J, I think J, it's a vector with 4 elements, numerical vector. So there's a unique mapping. These are called word embeddings. There's a unique mapping between every word and a vector. So when you provide the encoder with these words, you're not actually providing the words. Instead, you're providing these vectors, okay, multiple vectors. The encoders and decoders, they use recurrent neural networks. And we've talked about recurrent neural networks a couple of days ago. Recurrent neural networks, the way it works is, you start with an input, then your network generates a hidden state, and then it also generates an output. The network receives an input. I showed this, I believe, in the very first lecture, but typically recurrent neural networks work like this. You have some initial state. There is a network. It's a neural network. It receives an input, generates an output, okay? And then this neural network generates the next state. It goes to the same neural network, receives another input U1, generates the next output Y1, and so on. Okay. So this is a recurrent neural network because you're repeating these neural network structures. Okay. So that's what is being shown here. You start with a hidden state, input, output, and then you repeat this process. That's a recurrent neural network. And both encoder and decoder, they have these networks in them. Okay, so they receive the text from the left-hand side, and then they process the text through these networks. Okay. Now let's start this from the beginning. So there are 3 words. So you have 3 networks inside the encoder. They're going through these networks. You have one more network here. The inputs are the 3 words, right? What's the second SUI? Yes, and then there's a third word. And each of these generate hidden states. This is hidden state 1. This is hidden state 2. And here you have hidden state 3. Okay. Now only hidden state 3 is passed on to the decoder. Okay, not all hidden states are in this version, but we're going to modify it with self-attention. We're going to when we modify it, we'll see that the performance improves. So in this encoder, you're only sending the hidden state 3. That is the context that I mentioned earlier. Okay. And then within the decoder, again, you have the recurrent neural network that is spitting out I, am, a, and student. Right. So you have a similar decoder similar recurrent neural network in the decoder. It receives the hidden state, then it generates the first output is I, and then am a student. Okay, so this is the decoder. All right. Okay, the same thing. It's shown in a much more clearer fashion here. These are the recurrent neural networks. Encoder, the first recurrent neural network, second, third, and they generate those hidden states. Okay, is that clear? And each of these neural networks is outputting the translation of that French sentence into English. So I, the first recurrent neuron, am a student. Okay. Now, the problem with this approach is that if you look at this, only the last hidden state is passed on to the decoding state, right? In other words, other hidden states, you sort of lose the information that is available in other hidden states. You're passing only the last hidden state to the decoder. Okay. So this particular structure doesn't work all that well for translation. So that's where the idea of attention comes into play. Okay, so what if we can focus our attention more on certain words, depending on the context, right? Okay, and what if we can send all of the hidden states to the decoder instead of sending just one hidden state? Okay, so that's what this animation shows. So you have, instead of sending just one hidden state, as we did previously, we're sending all three hidden states to the decoding stage. And we make some modifications to these RNNs. These are called attention decoder RNNs. And the modifications are shown in the next animation. We can pause it here. Okay, so what are the modifications? You're modifying these recurrent neural networks to attention recurrent neural networks. Now, in this case, instead of sending just one hidden state from the encoder, you're sending all three hidden states. You take all three hidden states, you come up with scores of attention for each of those hidden states. For now, let's not talk about. Let's put aside how these scores are obtained. Let's suppose the scores are obtained. And then you generate what are called softmax scores. Do you know what softmax is? No? Okay. Softmax is, so in that case, for instance, you have a vector 13, 9, 9, right? Now this if you apply the softmax function on this, you will essentially turn this into a vector such that the sum of all the numbers in the vector is equal to 1. Okay? And the transformation is done as follows. See, your first element is exponent of 13 over the sum of exponents of 13 Okay, so this is the first element, and then the second element, you replace this with exponent of 9 there. That's the softmax function. Okay, so it turns any vector into a vector with numbers that are below 1, and when you add up all the digits in that vector, you get a 1. Okay. And then what you do is, so this softmax essentially highlights which hidden states are important. Okay. Now, in this case, 0.96 H1 is the most important hidden state. You multiply these softmax scores with the corresponding hidden states. So these are, I think this author is showing them in lighter colors because they have less weights. Okay, so when you multiply, you end up with something like this. Okay, and then you sum up all of those three vectors. Okay, instead of using the original hidden states, you modified them a little bit. You're paying more attention to one hidden state than the other hidden states. Okay, and that's done through this these scores. We'll see how these scores are obtained in the next page. Okay, so once you have the scores and then the softmax values,
you multiply the softmax values with the hidden states. Once you get the final hidden states, you add them all up, and that becomes your context vector that is passed on to the decoder. Okay, so this is where the idea of attention comes from. You're trying to focus your attention on the hidden state that has a higher score or more importance. Okay, so this here shows in this picture animation, he put everything together. Okay, you have all three hidden states come in, and then you have this attention mechanism that generates your hidden state, and you have this is the end token from the previous the French sentence. This generates a the next hidden state. You concatenate this token with the hidden state, and then you pass it through a neural network to generate your first English word, I. Okay, so that spits out I, and then you repeat the same thing again. Now, what's the difference between the original approach to translation and this? The main difference is this this attention mechanism. You're focusing at every stage of this recurrent neural network. You're focusing on a particular word. Okay. So here, if you focus a little bit here. The attention is on this hidden state. Over here, you will see that the attention is on the second state. Okay. So okay. See, the focus is on the second state. And so. Okay, so that's the attention mechanism. He has a nice matrix here that summarizes what is done through encoder and decoder. Encoder hidden state. You have 3 different encoder hidden states. When it's calculating I, the focus is on hidden state 1. AM and A, the focus is on hidden state 2, and student, the focus or attention is on hidden state 3, I think. Hidden state 3. Okay. Check this guy's blogs. There are lots of them, many videos as well. Really nice explanation. Okay, so that takes us to the architecture of transformers, right? Again, let's look at the same problem. You have a French sentence as input, and an English sentence as the output. And transformers have a particular structure that is very similar to the structure we had seen before, an encoder and a decoder. Okay. So in the previous example, our encoders and decoders, they have recurrent neural networks in them. In transformers, we use a slightly modified architecture inside encoders and decoders. So I'm going to focus only on encoders. We'll see how encoders are done, and decoders are very similar to encoders. Okay. Now, in deep transformers, you have deep networks. There's not just one encoder, but you have multiple encoders. Okay, so in this case, you have 6 encoders. There's nothing sacrosanct about 6. You can use 10, 15, whatever, right? So you have multiple encoders and multiple decoders. The output of the last encoder is passed on to all of these decoders. Okay, so here is where the the novelty comes in, right? In encoder, each encoder, you have a very specific structure. You have a network called self-attention, and another network which is feed-forward neural network, okay, standard feed-forward neural networks. That's the structure of each encoder. And the decoders have a slightly different structure, but very similar. You have a feed-forward network, an encoder-decoder attention network, and a self-attention network. Okay. Now, how is this done? Every word in any language is associated with a vector. J is associated with x1, which is a vector. Okay, it's not necessarily 4 by 1. It's probably 256 or 512 dimensional vector. It sues it to the end, right? So both of those words also have, in this case, these are called word embeddings. In this case, they're of size 512, meaning it's a 512 by 1 vector. Every word, French word, every English word, they all have a corresponding numerical vector that they are mapped to. So those abstractions or those mappings are unique, right? So you start with those words. They're mapped into, using these word embeddings, they're mapped into vectors. Once they're mapped into vectors, you're no longer dealing with words, right? You're only dealing with numbers and matrix multiplications inside these networks. Okay. So you start with your sentence, but right away you use your word embeddings, turn that sentence into these vectors, and the vectors then are passed on to the self-attention module. Okay. Now, in this example, he's moving away from that sentence just to keep it simple. The sentence he has here is thinking machines. Okay, so 2. Within the encoder, I believe in self-attention, there is some cross correlations between these two words that happen. But in the feed-forward network, you can do parallel calculations for each of these words. Okay, there are separate feed-forward neural networks for each word. So you pass this through this self-attention layer that generates a hidden state, which is then passed on to a feed-forward neural network, which generates a hidden state that goes to encoder number 2 and so on. Okay, here it gives a very nice example here. So what is self-attention? What are we trying to do, right? Take a look at that example. The animal didn't cross the street because it was too tired. Okay. Now, we understand that it refers to the animal, but the machines don't, right? So you have to figure out a way to correlate it with the animal. Okay, so that's what we're trying to do using self-attention, using those vectors. We want to connect this it to the animal. That's the most correlated phrase in the sentence. It does not refer to the street. Right? It refers to the animal, and your algorithm somehow needs to figure out that is the case. Okay? And it is going to do that by paying attention to the first two words, the animal. Attention is, in other words, attention is simply correlation. Okay, so it's as simple as that. Okay. There's a lot more to this, but at a very high level, I'll show you how the self-attention mechanism works. We have a different sentence now, thinking machines. You do word embedding that generates your x1 and x2, two vectors. Then when you train the model, you create these matrices. These are called query, key, and value weight matrices. you multiply the embedding vector with each of these matrices to generate what are called queries, keys, and values. Okay. All of these vectors are combined to generate the output of the self-attention module. Okay, so you start with thinking. X1 is the word embedding, and then you use those query, key, and value matrices to generate the new vectors Q1, K1, and V1. Then you multiply the query vector with the key vector to get a score. So remember I talked about score in the attention mechanism, and I didn't tell you how those scores were obtained. This is how they are obtained, right? So each you get a score for thinking. Not just for thinking, you also get it for machines. When you're dealing with the word thinking, you get a score for thinking and machines. So this is in a way, one way to think about it is you're calculating the correlation of the word thinking with itself and also with other words in the sentence. Okay? So the higher the correlation, the higher, in some sense, the attention of that word to the corresponding other words in the sentence. Okay. And then there are some other procedural things that you go through. You divide these by 8, and then you apply softmax. Softmax is that exponential function. Okay, after softmax, you multiply that with the value vector that gives you a new set of vectors, and that gives the output of the self-attention mechanism, which is Z1. So if I go back to this picture, here it says Z1, right? So that's how Z1 is calculated. You repeat that for Z2, and then you pass them through this feed-forward neural network to generate new states. Repeat this process with the next encoder. Okay. Now here we have used simple sentences with just 2 words. If you have a lot of words, you'll have to use matrix calculations. Softmax, it's all the same. Yeah. So I think that I'll stop there. I mean, the rest of it is you repeat the same things through the encoder, or through all the encoders, and then you repeat them through the decoders to eventually get your translated word. Okay, so there's. I'll pause there and take any questions, but that's essentially what attention mechanism is, and this particular structure is the transformer. Where is it? Here. Yeah, so this is, sorry, this is the transformer. Right. Now, something like Chat, I mean, nobody knows what ChatGPT is using because it's their proprietary technology. But this is a language model when you use billions and trillions of parameters in lots of encoders and decoders, then you have a massive model. Facebook, the publicly released large language model has I think about over 400 billion parameters. So you have all these encoders and decoders with lots of parameters in them. I believe there are models now, maybe ChatGPT has 1 trillion parameters, right? We don't know. They don't release that information, so we don't know. Imagine training these models, right? So we talked about simple back propagation, et cetera, earlier. And now imagine training 1 trillion parameters. It's a massive optimization exercise. I believe OpenAI spends over $100 million to train this model once. And that cost includes the cost of engineers, the cost of running their computers, and all that stuff. Right? So it's very expensive to train these models, and you need enormous computing power. In the U.S. right now, some of these companies are investing. OpenAI, Amazon, Tesla, Facebook. They're all investing in really massive high-performance computing centers with NVIDIA Blackwell chips, B200 and other chips that are meant specially for AI, for training AI models. So check out Sebastian Rachka and this Jay Almar, I think is his name, Jay Alamar. He has lots of YouTube videos as well that are excellent. Okay, so I'm going to stop there. So we have about 15, 20 minutes. If you have questions, anything you want to ask, I'm happy to take your questions. Did anyone try the Python notebook this morning, advanced learning? No, not yet.
Professor, I have a question actually.
Yeah.
So I think it's nice of good overview of transformers or LLMs. So we wanted to, as a chemical engineer, wanted to see where can we find this LLMs application in process industry.
Yeah.
Can you just give a brief outline of it actually?
Yeah, there's some really good applications. One, what's his name at NTNU? Arthur Schwarzman, I think. He gave a talk in my research group. He's looking at P&ID diagrams, process and instrumentation diagrams, with lots of text and diagrams. He's using LLMs to interpret those diagrams, I think. I don't remember exactly the problem, but he's using this with the process P&ID diagrams. That's one application. We have used it. One of my students used LLMs to interpret time series data. So what he did was, this was in a clinical setting in an emergency department. When patients come in, I explained this on the first day. When patients come in, they measure their temperature, blood pressure, oxygen levels, etc. And then nurses, based on those heartbeat, they measure those, and nurses determine the status or state of that patient. They typically have a description of the patient's condition. So we built a small language model, not a large language model, that takes the time series data and generates a description of the patient's condition, right? Just like what nurses would do today. Yeah. We labeled approximately 15,000 data points. So the data that we had was not labeled, meaning we did not have the description of the patient with their measurements. So we knew, so for each patient, we knew heart rate, temperature, blood pressure, oxygen levels, maybe a couple of other things. But the description of that patient's condition is not there. So one of my students and a nurse at Vancouver General Hospital, they spent over 6 months taking each of those data sets, data points, and describing them in words, right? So they labeled like that some 15,000 data points, and then they use that data to build a small language model, which we are hoping would help in the emergency settings.
Thanks.
Thank you.
And if, let's suppose if we are using this LLMs for a time series forecasting or prediction, like in chemical process, like fouling prediction. We wanted to predict the fouling of a particular reactor
Right.
much earlier when compared to actually the actual event happens.
Right.
Okay, so in those cases, can we use this because they can predict for a longer range predictions? Can we find any applications there actually where like maintenance, predictive maintenance?
I mean, that's a great question, right? So when language models were released almost a year and a half ago, one of my students, he works at Amazon. He was very familiar with their foundation models and so on. So he came to me and he said, I can replace controllers with a language model, right? So, and shockingly, he was right because he just replaced the controller with the language model. The language model was taking time series data and generating a control action, right? Okay. He tuned it. I don't know the details, but he tuned it. And that was a big eye-opener for me. And later, there are a lot of others who have similarly used large language models for classification, for instance, or regression. And they found that language models are performing better than everything else we learned. Support vector machines and other models. But nobody understands why, right? Obviously, you don't want to spend $100 million and build a large language models to tune a controller.
Correct.
So, but having said that, I think there was an interesting presentation by somebody from New York University math department at the NeurIPS conference in December in Vancouver. And he was saying language models have the potential to become universal models, meaning they'll probably work with any system you have. But then the downside is they're expensive, they're massive, and who wants to, how are you going to deal with that complexity, right? When the problem is so simple, do you need that? So I think, Jairam, I think there are some really cool applications that are coming out in chemical engineering. We might, if things work out, we might organize a large language model workshop at IFAC World Congress in Korea next year.
That's good. That's nice. Yeah. So then last one, I think. So you said the computational intensity is a major backdrop of this one.
Right.
So, but I think if let's suppose we are implementing this for a process, industrial process, but process conditions change over a period. So how a regression model can be adapted easily if I want to adapt the model in real time, or the parameters need to be adapted.
Right.
So will the transformer model can be adapted in real time actually? So will that
Right. I mean, that's a great question. I don't know the answer. I mean, can we adapt it? I don't know. I mean, I don't know how adaptation works with these models. I mean, it's difficult enough with simple models. With something like this, can you adapt on the fly as you get new data? I'm not so sure. You may have to redo the whole thing, right? I don't know if an answer to that exists. It's probably not possible with them. The structure might have to change. It's not clear to me how you do that.
Thanks, Bhusan.
Okay, no problem. Thanks a lot. Okay, so are we done? I mean, I'm done with what I wanted to teach. I can talk about a lot of other things. If there are no questions, I will hand the stage over to Jairam. He has some really cool things to teach you today and tomorrow. I know, it's a lot of stuff. Right. Yeah, totally understand. In your position, I will also be overwhelmed. It's easy to understand. When I tell you, you multiply this with this, you understand that, right? But if you want to get the bigger picture, you zoom out, it's not that easy. You may understand each and every step that I showed you, but then what's the bigger picture? Why are we doing what we're doing, right? That takes some amount of meditation on the topic. But the strange thing is, there are computer scientists who are very theoretical, right? They do a lot of very rigorous theoretical work. In control and other electrical engineering areas, again, we do a lot of very theoretical work, like systematic, rigorous, and there are proofs for everything, every statement we make. But with these large language models, what we know is they work. But can we guarantee theoretical limits, etc.? Nobody knows. And in fact, nobody knows why these models work. Right? But they seem to work. OpenAI released a new reasoning model. Have you heard of reasoning models? No. Okay, so ChatGPT, the original version, it's not a reasoning model, meaning you give it a prompt, it spits out a response. The reasoning models, they actually take you through the thinking in their brains, right? So it'll say, if you ask it a question, for instance, on Claude this morning, I was asking it something and said, I'm searching the web. I found this. This seems to be appropriate for your question, and therefore I'm doing this. So they take you through that, right? Those are called reasoning models. So very strangely, when OpenAI, they went from GPT-2, 3, and then 4, I think there was for GPT-O or something like that. And then they released a reasoning model. And the reasoning model had far worse errors than the previous models. Have you heard of hallucinations? So these models, I don't like the word hallucinations because it makes you feel like it's a living thing. It's not. A hallucination is essentially a probability, right? So these models are working based on probabilities. They use softmax, right? Softmax is like probabilities. So there is a probability of picking the wrong output, which is called hallucination, right? Yeah. So the new models, reasoning models, apparently had higher number or larger number of hallucinations compared to the previous non-reasoning models. Now the problem is nobody fully understands mathematically how these things are working. That's a challenge. Yeah, so you take typically image, you have red, blue, green pixels, right? So and then there is pixel intensity for each of those colors. So those intensities become your vectors, RBG vectors. Yeah. So now you have numbers, right? So you're going from image to numbers. Self-attention, and it's the same thing. Yeah. I mean, in my mind, attention is essentially correlation, right? Correlation. So what you're trying, as I mentioned in that example, the animal is crossing the street or something like that, and then there's an it that refers to the animal. Now, when the machine is interpreting it has to understand that it refers to the animal. Okay, so that's the idea of attention. So the correlation between it and animal is going to be higher. Okay, I think so. Yes, go ahead. Oh, thank you. I mean, it's been my pleasure interacting with you. Yeah, great. Yeah, exactly. That's exactly what I'm hoping we have achieved. And as long as as long as we've sown the seed of machine learning in each and every one of you, I'm confident you can take it from there and do amazing things in your research. Yeah. Yeah, of course. I should thank my students. In all my slides, it says Eating Sai, Liripan, and Aditya Tulsian. So they were all my students. Eating Sai is, he finished his PhD, he's now working in Vancouver, very smart guy. And then Liripan also, he graduated at the top of his class from my department, then he did a PhD with me. He now works for a subsidiary of Emerson in Calgary. Aditya Tulsian, one of the smartest people I know. He actually was a grad student at University of Alberta, but he worked with me during his PhD. Then he finished his postdoc at MIT. He's now working for Amgen. So it's really these three students who created those Python notebooks. So all credits to them. Yeah, thank you. Yeah, we should. Yeah. Thank you. Do you have a question? No? Okay, so I think we're done then with that. Thank you very much. I wish you all the best in your PhDs or masters undergrads.
Okay, we would like to thank Professor Bhusan Gopaluni sir for his sharing all his ideas and lectures, notes with us. And sir we can able to communicate with sir at any cost of the time. So sir will be responding to the mails, but not so reasonable queries sir will be responding it, okay.
Okay, somebody, one of your students, I'm trying to remember who was that. I think it was your student. She sent me an email apparently in November, and I never responded. So we searched through my email. It was unread. So she was surprised. So I mean, part of the challenge is I get a lot of email from, our email addresses are open to the rest of the world. There's a lot happening, and I naturally focus on emails that I get from people I know. So if you send an email, the subject line, write Gian, so I'd recognize who you are. If I don't respond, feel free to send me a few reminders. And I do make it a point to respond to students especially. But sometimes, depending on time of the year and what I'm doing, it might be difficult. But please send me emails and remind me that we met at this workshop.
So on behalf of, as Sandeep told that on behalf of VNIT and behalf of the participants, I would like to thank you for spending your valuable time with us.
Thank you. I want to thank Surinder and Joydeep and the rest of the people who have made this workshop happen. Thank you so much. I think these interactions are absolutely vital. When just coming here and talking to you, I realize that there is so much that some of us have been exposed to, and I think I particularly enjoy transferring that knowledge back to the students, whatever we know, the limited things that we know. It's been an absolute pleasure working with you.
Yes, sir. Anyway, today you are leaving. Sir is leaving today at 4 o'clock. So our one more guest is there, esteemed guest, Jairam sir from IIT Roper. Okay, so even though he is available tomorrow, but sir is leaving today, so I request him to welcome through by sampling to him. Yeah, Jairam. Please. Yeah, please. Come now, sir. Tomorrow we'll have a formal welcome, but this is for Sir is leaving today.
All the best.
Thank you. Okay. Okay, sir. Thank you, sir. There is no word.
Thank you. Yeah.
We could not able to express our thank you in terms of words, whatever you would like to say.
Thanks a lot. Yeah.
Now we'll wind up some time for tea break. Then we'll just join at 4 o'clock, 4 to 5. Then tomorrow Jairam sir will be taking over the sessions for next in the Bayesian networks in soft computing.
All right. Thank you.
Can
Yeah.
I personally-
Yeah.